In previous videos, we have seen that the precipitation of salts within porous materials can lead to damage, and that there are similarities between that process and the crystallization pressure of ice during the freezing of water in such porous materials. Here, we assume that you have watched the video on crystallization pressure of ice during freezing. In this video, we examine the chemo-poromechanics of crystallization pressure of salts, underlying which conditions may lead to damage. We consider the case of a large spherical pore of radius Rp, filled with a supersaturated solution and connected by two cylindrical pores with an entry radii Re containing the same solution. Let's assume that a spherical crystal nucleates in the large pore, grows, and that ions are supplied to maintain the supersaturation. This crystal will grow until it almost fills the pore, leaving a liquid film between it and the pore wall with a thickness delta in the nanometer range. This film is due to repulsive forces between the crystal and the pore wall. Should additional ions from that film deposit on the crystal, they would bring its surface too close to the pore wall, which is thermodynamically unfavorable, so that they will jump back into the solution. Crystal growth in a solution is driven by supersaturation. For a crystal with a composition capital A, small a, capital B, small b, the solubility product, Q, is activity of A to the power small a times activity of B to the power small b, where activities can be approximated by molar concentrations and denoted with square brackets for dilute solutions. For a reminder on this, please view our video on chemical thermodynamics. For a crystal so large that its curvature is negligible, equilibrium is reached for a certain value of Q called the equilibrium constant and designated by K, and that is a function of temperature. The solution is supersaturated if the concentration of ions is high enough to make Q greater than K. The crystal, in our example, will bulge into the connecting small pores, adopting a curvature, kappa Cl, linked to the supersaturation ratio, Q over K, of the pore solution through the Ostwald-Freundlich equation, which states that the curvature, kappa Cl, is equal to R, the universal gas constant, T, the absolute temperature, divided by gamma Cl, the crystal liquid interfacial energy, Vc, the molar volume of the crystal, times the natural logarithm of the supersaturation ratio, Q over K. This equation means that a flat crystal, where kappa Cl equals 0, is in equilibrium when Q equals K. However, a curved crystal is in a higher energy state than a flat one because a larger fraction of its atoms is at the surface, so it will dissolve unless Q is larger than K. For the crystal to enter into the connecting pores, its curvature must be at least kappa Cl at the entry equals 2 over Re minus delta, which requires a supersaturation satisfying the following equation. Natural logarithm of the supersaturation at the entry equals 2 gamma Cl Vc over RT times Re minus delta. If the solubility product Q in the solution equals QE, the crystal will just fit into the small pore entries. If Q is larger than QE, the crystal will propagate along those pores. In our example, the large crystal is so big that its curvature is negligible, so it is in equilibrium when Q equals K. However, as Q increases towards QE, the crystal will tend to grow. However, since the pore wall blocks that growth, there is a crystallization pressure on the wall given by P equals RT over Vc times the natural logarithm of Q over K. The growth of the crystal is resisted by a radial compressive stress, sigma r, of equal magnitude exerted by the porous matrix onto the crystal to prevent its growth. This stress goes along with a tensile circumferential stress that is particularly damaging to materials that are weak in tension, as stone, brick, concrete, and adobe. This tensile stress can be understood considering a person putting on a belt. As the belt compresses the belly, it exerts a radial compressive stress on the belly, but the belt itself feels a tensile hoop stress. It can be shown that the crystallization pressure, P star, needed to damage a porous material is given by P star equals sigma T, the tensile strength, over B, the BO coefficient, times the square root of 3 times 1 minus 2 times the Poisson ratio, all of this times 1 over SC, the fraction of pores occupied by crystals exerting that pressure. For Indiana limestone, a useful reference of a sedimentary building stone, the tensile strength is 2.7 megapascal, the BO coefficient about 0.74, and the Poisson ratio 0.26, so that we find that P star is more or less 3 over SC. For our example, this implies that if 30% of the pore space of the stone is filled with salt, then damage will happen if the pressure reaches at least 10 megapascal, which is the value of P star for SC equals 0.3. For sodium chloride, with a molar volume of Vc equals 27 cubic centimeter per mole, the crystallization pressure is roughly P equals RT over Vc times the natural log of the supersaturation, which implies that a P star of 10 megapascal is reached for a supersaturation of 1.12, making it possible for damage to occur. This value is not particularly high, so one may expect such situations to happen in practice, but specific conditions are nevertheless needed for this. For example, our analysis assumes that our crystals are trapped within large pores surrounded by small pores. The radius of these may be estimated using our previous relation between saturation ratio and pore radius, which was that the natural log of the supersaturation at the entrance is 2 gamma Cl Vc over RT times Re minus delta, which, with the crystallization pressure equation, would give that Pe is equal to 2 gamma Cl over Re minus delta, where the superscript E indicates the pressure reached just before salts propagate through the pore entries. For our example of sodium chloride in Indiana limestone, where a pressure of 10 megapascal would have to be reached for damage, and considering an interfacial energy gamma Cl estimated between 10 to 60 millinewton per meter, with a film thickness delta of about 1 nanometer, we find a pore radius Re of about 3 to 13 nanometers. This is much smaller than the pores in most building stones, implying that our crystal trapping mechanism is not likely to present much risk of damage. Salt damage usually occurs in slightly more complex situations, as developed in our next video. For cementitious materials, the above pore size is realistic, but we would need to consider other material parameters in addition to curvature effects, which we will do in our videos on sulfate attack. In conclusion, crystallization pressure develops at the pore scale depending on the available supersaturation. This leads to a macroscopic tensile stress that is proportional to the degree of pore filling and is particularly damaging to materials with small pores that are weak in tension. A critical stress above which damage takes place can be defined when considering simple pore geometries. In practical terms, removing salts will be beneficial as long as the macroscopic stress remains below the critical damaging stress.